Okay, so these slides we will try to let you know how to derive the differential form of the Maxwell equation. Actually, in the previous lecture, we only covered the integration form as in the textbook. But actually in chapter 33, I'll say if you don't know how it is derived, how the wave equation is derived, you will just see quite a lot of equation, and then you don't know why it will be like that. So that's why I here try to derive the differential form of the Maxwell equation, and then based on this differential form of the Maxwell equation, we can derive the wave equations, and then by solving the wave equation, the solution of it will be the EM wave. So that's why we need to supplement the math up to this point. Okay, so this is the outline. So the first part, the differential form of the Maxwell equation, and then tells you two of the theorem in multivariable calculus. So one is called the divergence theorem or the Gauss theorem. So you can simply expect that this Gauss theorem is related to the Gauss law. Okay, and then also the Stokes theorem. Okay, it will be useful for the Ampere's law and also the Faraday's law. And then finally, I'll also talk about the conservation of charge. Yeah, because in chapter 32, we introduced the idea of a displacement current, which means that for the Ampere's law that we have learned in chapter 29, we only have a single term on the right side. That is mu 0 I enclosed. And then here, okay, in chapter 32, we say that, okay, there should be something like something called the displacement current, and then add it to the right side of the Ampere's law, known as the Ampere-Maxwell's law. So adding the second term make it more correct, and then maybe you have a question that whether we can add even the third terms, fourth term to make it even more correct. The answer is no, because up to this stage, okay, the Ampere-Maxwell's law have two terms on the right side, and actually it will consistent with this conservation of charge. Yeah, if we even add more terms, then it will violate the conservation of charge. So yeah, so this is some mathematics behind it. Okay, so here is the integral form or the integration form of the Maxwell equations, just as what you have learned. The Gauss law in chapter 23, and then Gauss law for magnetism in chapter 32, and then Faraday's law in chapter 30, Ampere's law in chapter that this Ampere's law also learned it in chapter 29 and chapter 32. Okay, so depends on the first term and the second term on the right side. Okay, so so here we try to slightly modify this phi b phi e. Okay, actually we have learned this. Okay, so actually the phi b is the magnetic flux. Okay, the magnetic flux. So this phi b can be written as this surface integral. Yeah, of course, it is just a surface enclosed by an Amperean loop. So this is not a closed surface. We don't have a circle on the right side. So this is different from this one. Okay, although this one and that one are also integration of b dot dA, but this one is for Gaussian surface. These two are for Gaussian surface. So we don't have a circle here. Okay, likewise, for this phi e, okay, we can also rewrite it as the surface integral of e dot dA. Okay, so nothing special. I think up to this moment, up to this part, yeah, you have already learned it. Okay, but here we also try to make some more modification. So first, okay, so actually for the Gauss law, we originally have Q enclosed on the right side. Here, okay, actually, actually most of the integration side we also try to rewrite. In the textbook, in the textbook we are using, so all of the integration side use the single integration. But if you just check out other material or the mathematics textbook, they will try to separate it, write it in a more precise way. So let's say for the Gauss law, okay, this one is a surface integral. So we should use two integral sign, okay, to refer that this is a double integral, okay. So this is a surface integral, or double integral, okay. Double integral. So we need to use two integration sign to specify that. Okay, so this is an area, okay, in two dimension. Okay, so maybe I first skip this part first. Okay, I'll come back a bit later. So similarly, this one is also double integral, or surface integral. So we use two integration sign. So as this one, okay, although we don't have a circle to specify that it is a closed surface integral. Okay, this is not a closed surface integral, so we only have a double integral sign. And okay, so here, go back to here. So for the Q enclosed is a charge enclosed by the Gaussian surface. So actually, we try to write this Q enclosed as a triple integral. So that this one is charge density. Okay, and then dV. Okay, so dV is a volume. So this is a three-dimensional stuff. Okay, so we need to integrate the charge density over a volume. Okay, this volume is actually the volume enclosed by the Gaussian surface. So this triple integral will be the total charge enclosed by the Gaussian surface. Okay, so this is still okay. Maybe we already seen it in chapter 23. So this one is nothing special because the Gauss law for magnetism is has a zero on the right side, and for this one, for the line integral, we don't need to change because for line integral this is a one-dimensional integral, so we still keep it a single integral sign. Yeah, and here for the I enclosed, we try to rewrite it as the surface integral of the current density. Okay, so different from the textbook, we use a double integral sign. Okay, so to specify that this is a surface integral. And yeah, so this is pretty much like that. So finally, the integral form of the Maxwell equation are rewritten as this one, and this one. Okay, so actually this is actually the same as this one. Okay, so you just try to make it more precise. Okay, so this is the Yeah, this is the answer. So this will be the differential form. This will be the differential form. And then for the differential form, you'll see, okay, so this is the upside down triangle. Okay, so in chapter 24, we have seen this one occurred, without the dot product or cross product behind it. Okay, so for that one, we call it gradient. Okay, we call it gradient, but here we have a dot product after the gradient, and we also have the cross product after the gradient. Then we will call this whole thing to be divergence. Divergence in Chinese, 散度. And then for this one, we call it curl. Okay, we call it curl. Okay, I forgot the Chinese name. Okay, but actually never mind. So anyway, so this is the answer. But yeah, how can we derive it? Okay, but so before knowing the mathematics behind it, you can just by observation you can recognize some similarity here. Yeah, because on the left side, okay, just look at these two: Gauss law for magnetism, and then Gauss law. Okay, so on the left side, surface integral of the E dot dA, surface integral of B dot dA. So both of them turns into gradient dot E, gradient dot B, okay, or divergence of E, divergence of B. Okay, so this is the left side. And then for the right side, okay, so we just skip this integral side. Okay, so only the rho over epsilon naught on the right side, rho over epsilon naught on the right side. And then here, 0, you can consider it as a triple integral of 0 dv. Okay, integrating a 0 over and over again is still a 0. So you can see the similarity. So on the right side, we only have the 0. And then for the third and fourth, for the Faraday's law and for the Ampere's law, on the left side is the line integral for E field and the line integral for B field. Turns into the curl of E and then curl of B. Okay, so you can see the similarity here. And then also here is like, okay, we try to skip the integration sign. So here we only have dB dt, okay, negative dB dt, yeah, but B is a function of x, y, z, and t, okay, so it's has a multi-variable, multi-dependent variable, okay, so multi-independent variable, okay, so we should use a partial derivative rather than the ordinary derivative. Okay, so here also skip the integration sign. We have mu j. So mu j, and then okay, finally we have a mu epsilon naught d dt. Okay, E. Okay, so finally epsilon naught partial E partial t. So you can also see quite a lot of similarity. Okay, so these two is a group. 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 Okay, so when we try to put them together, it will be like that. So the integration form of Gauss law, surface integral of E dot dA equals 1 over epsilon naught triple integral rho dot dV. Okay, so the charge density for the triple integral of the charge density divided by epsilon naught will be the electric flux, and then this one, the magnetic flux, is always 0 because we don't have a monopole, we only have a magnetic dipole. And then here, Faraday's law, so this is the induced EMF, will be the negative of the rate of change of the magnetic flux. and then here Ampere's law will be mu naught times the current, static current, and then this is the displacement current, the epsilon naught times the rate of change of the electric flux over the Ampere loop. Okay, so compared to the differential form, divergence of E equals rho over epsilon naught, and then divergence of B equals 0, and then divergence of this is curl of E equals negative partial B partial T, and then curl of B will be mu naught J plus epsilon naught partial E partial T. Okay, so far, okay, so it is like, what is this? What does it mean? Okay, so we will start to talk about it. Okay, so actually in chapter 24, I've mentioned that, okay, so this is the gradient operator. The upside down triangle is the gradient operator. So which means that this one is the operator, means that it cannot occur by itself, okay? It need to have some operand, okay? It need to have some operand to work on this operator. Just like when you learn add, okay? Addition, okay, in primary class, okay? So addition is the operator, 那个加号, okay? It's the operator, so it need to have two operand, okay? So A plus B, okay, A plus B. So it need to have A, B as the operands, so to work on this add operation. And then for this one, okay, this operator only have one operand. Or maybe you also have learned some operand that only has one operator that has only one operand. For example, sine, okay, sine only have one operand, sine of something, okay, equals another value. Or maybe factorial, 阶层, okay, factorial also have let's say 4 factorial, 3 factorial, or maybe you can just go to some 1/2 factorial is also fine, okay. Okay, actually Euler's try to extend the factorial into real number and even the complex number. So you can actually have half factorial. That will be square root of pi over 2. Okay, so anyway, just off a little bit. So anyway, so this is the gradient operator, which means that, okay, it should follow by some scalar field. Okay, so this gradient operator should follow a scalar field. In that case, in chapter 24, what we learn is actually E equals negative gradient V. Okay, so this is the scalar field. Scalar field. Yeah. And then, okay, after the operator, okay, it become a vector field. Okay, so on the left side would be a vector field. So actually in the Cartesian coordinate, so this is Cartesian coordinate. Okay, so in other coordinate system, the expression will be quite complicated. Okay, so difficult to remember. But for Cartesian coordinate, at least x, y, z are independent to each other, so it turns out to be quite elegant. Okay, it will be like a partial x, and then the unit vector of x-axis, and then partial y, the unit vector in y-axis, and then the partial z, and then the unit vector of z-axis. So yeah, so you need to operate to a scalar field behind it. Okay, so here we also have the divergence. Okay, so we have divergence and the curl. So first we talk about the divergence, so which is like a gradient with a dot product. Okay, you can actually understand it like this. So let's say we have generally a vector field F, which can be written as Fx, F sub x, and then I hat, and then plus F of yj hat plus F of ck hat. Okay, so generally, okay, you can imagine this F can be an E field, can be a B field, can be any other vector field. Okay, so if we try to take the divergence of F, okay, divergence of F, it turns out to be partial Fx, partial x plus partial Fy, partial y, plus partial Fc, partial z. Okay, so the reason is very simple. We try to, yeah, of course, this is the Cartesian coordinate, this is also the Cartesian coordinate, so it is like divergence of F is actually partial x I hat plus partial y j hat plus partial z k hat, and then dotted with so we have f sub x I hat plus f sub y j hat plus f sub z k hat. Okay, so you need to distribute. Okay, so this one distribute to this 1, 2, 3 term, this one distribute to this 1, 2, 3 term. So altogether we will have 9 terms. Okay, so you need to expand it, but hopefully, as we have already learned, okay, I dot I will be 1, j dot j will be 1, k dot k will be 1. Otherwise, will be 0. I dot j will be 0. I dot k will be 0. So which means that only I dot I will be 1. Okay, so it turns out to be partial x, fx, and then this one and this one dotted will be a 1, so it will be partial y fy, and then also we have this one dotted with this one, turns out to be a 1, so we have partial fz, partial z. Okay, so this is nothing but this one, so it's really easy to understand. And then actually it's like a dot product, so which means that the divergence of a vector field, okay, turns out to be a scalar field. Okay, turns out to be a scalar field. This is a scalar field. We don't see any vectors here. Okay, so fx, fy, fc are just the xyz component of the field. Okay, so it makes sense because when we have the dot product between two vectors, it turns out to be a scalar. Okay, so here gradient is like a vector operator dotted with a vector field, turns out to be a scalar field, so it totally makes sense. Okay, so what does it mean? What does it mean for the divergence of f? So if a divergence of f, just as what I mentioned, is a scalar field. It's a scalar field. What does a scalar field means is that it has value. Okay, so actually it can be a function of x, y, z, and t. X, y, z, and t. Okay, so this is a function of x, y, z, and t. So which means that given a set of x, y, z, and t, maybe this point at this moment, okay, it has a value. For that point at another moment, okay, it has also has a value. Or maybe fixing a point, and then when the t change, maybe it has the same value, or maybe it has different value. Depends on whether the environment changes or not. Anyway, so it actually means that, okay, this is a scalar field, which means that if you just plug in x, y, z, t to this divergence of f, you can check the divergence at that point and at that moment. Okay, if that value is greater than 0, it means that this vector field f, okay, this vector field f tends to spread out, okay, from that point. Okay, so try to going out from that point. And if the divergence of f at a certain point is smaller than 0, it feels like the vector field f is going into that point. Okay, if this divergence of f is equal to 0, it means that okay, it is not either going in or going out for that point. Okay, maybe some of the field is going in, some of the field are going out, and then they perfectly cancel. So yeah, so this is what the divergence mean. Okay, so this is the divergence, and then we also talk about the curl. So for the curl, okay, the curl with a cross product, you can imagine it is a little bit more complicated. Okay, I remember. Okay, the Chinese name, it is called 旋度. Okay, I remember. Okay, so similarly, we try to assume a general vector field f to be fx I hat plus fy j hat plus fz k hat. Okay, so this is a vector field that you can imagine whether it can be E field, B field, or whatever field you want to be. Okay, so here, okay, if we try to compute curl of f, so first, of course, you try to write out the gradient. Okay, the gradient in Cartesian coordinate, and also this f in Cartesian coordinate. Yeah, of course, in other coordinate system, okay, the expression will be quite strange. Okay, so but anyway, for the Cartesian coordinate is at least quite symmetry. Okay, quite symmetry it will be easier to understand. Okay, so here we have a cross product in between. Okay, so to compute this cross product, okay, with this Cartesian coordinate expression, of course you can still distribute. Let's say, okay, picking up the first term, okay, you cross with the first term, the second term, and the third term, and then next one, okay, pick up the second term, cross with this one, and this one, and then pick up the last term, cross with this one. Turns out to be 9 terms, and then 3 of them will be 0, because I cross I will be 0, j cross j will be 0, and then k cross k will also be 0. But for other combination, let's say I cross j will be k, j cross I will be negative k, so on and so forth. Okay, of course you can just try to just try to expand it. Okay, but here we can just try to make use of the determinant. Okay, 就是利用这个行列式 okay for this 3-dimensional case. It works. Okay, so don't try to ask why it's correct, because it is correct. Okay, so the idea here is we try to write ijk in the first row. Okay, ijk in the first row, and then we have one vector cross with another vector. So for the first vector, we have a xyz component. So we try to put the xyz component for the first vector on the second row. Okay, so we try to put here, and here in the second row. And then for the second vector, it also have a xyz component, or this one, we try to put it in the third row. Okay, this turns out to be a 3x3 matrix, the determinant of the 3x3 matrix. So for this 3x3 matrix, it is easy to calculate. 4x4, much more complicated. Yeah, because for a determinant of nth order square matrix, okay, it will have an n factorial term. So for 3x3 determinant, okay, it will have 6 terms. But for 4 times 4 determinant, it have totally 24 terms. Okay, 24 terms. Okay, so anyway, how we can calculate it? So to make the computation look easier, so it is like, so it only works for 2 times 2 and 3 times 3. 4 times 4 is not that. Yeah, because you imagine, okay, it's only have 8 terms, but not 24 terms. Here, the idea is we try to draw a line, okay, like this, 1, 2, and 3, okay, so they are positive, okay, they are positive, which means that we have I hat partial y fc, okay, which is partial y fc, which is this term, okay, which is this term. So this is the first one, okay, this is the first term. And then the j hat partial z fx will be this term, okay, so this is 2, this is the second term. J hat partial z fx here goes to here. And then k hat partial x fy, okay, so this is the third one, okay, maybe I just remove this one, okay, so this turns out to be k partial x, k partial x, and then fy goes to here. So this is the third term. All of these 3 terms are positive. And then let me try to change another color. Let's make it green. So here we try to draw 3 lines also. So this one, and also this one. Okay, so all of them are negative. Okay, so here we have a k partial y and then fx. Okay, so this will be that one, but with a negative sign. So this is the fourth, okay, the fourth one goes to here. And then j hat partial x fc, okay, so this one is j hat partial x goes to here, and then fc goes to here. So this is the fifth term, okay, the fifth term goes to here. And then finally I hat partial z fc, okay, I hat here partial z, and then fy, okay, fy. So this is the sixth one, okay, the sixth term, okay. So by making use of this determinant, we can quickly write out all the 6 terms, okay, like this. Or maybe it is just like I hat will be like this one multiplied together, okay. So it is like I hat, and then we have this one partial y f z partial z f y, okay. So they are like this is positive, this is negative, this is positive, this is negative. I had partial y f z, this one minus partial z f y goes to here, so on and so forth. Okay, anyway, so this is the expression of the curl operator, okay, in Cartesian coordinate. Turns out to be these 6 terms. Looks more complicated than the divergence. So what does it mean? Okay, in Chinese called 旋度. So you can imagine it's trying to describe how the vector field of F is rotation. Okay, it's rotating. Okay, so anyway, so curl of F takes this expression. So here's an example. Okay, suppose we have a F xyz. Okay, so independent of t. Okay, we just assume that this vector field does not change with time, so only related to the xyz. So it is like y I hat minus xj hat. Okay, so it is hard to imagine what is it like. So here we try to plot it out. Okay, but it is a vector field. So the idea here is we try to pick some point. and then try to draw an arrow at that point, specifying the direction and also the magnitude at that point. Okay, so of course the arrow points to the direction of the vector field at that point, and also if the vector is has a larger magnitude, the arrow is longer. So you can imagine, let's say we plug in x to be 0, x to be 0, y to be 1, okay, which is, or maybe y equals 2, okay, which is actually, let's see here, so this is the x-axis, no, okay, so this is a little bit strange, okay, this is, okay, so, oh, okay, yes, this is x-axis, this is y-axis, okay, so if x to be 0, y to be 2, it is actually this point, this point means if we have x to be 0, y to be 2, so which is actually 2i, which means that for this point, okay, it's actually point to the right side. It's actually point to the right side with a magnitude of 2. Or if we have x to be 2, y to be 0, which is actually here. So if x equals 2, y to be 0, this is 0, and then minus 2j. So which means that at this point, this is pointing downward. Okay, so for every point, you can just plug in the number. You can see what this f is at that point. Okay, so, and then this graph already tells you that, okay, more or less like that. So it will be like close to the original point, it is weaker, yeah, because these two components are related to the coordinate. Okay, so if x, y are larger, then you can imagine this f is larger. So you can see close to the origin is small, and then far away from the origin will be larger and larger. And then for the direction, okay, this point to the right side, point to the downward, point to the left side, pointing upward. So it is like rotating clockwise. Okay, so if you just plug in this thing into this expression, of course you need to do some computation, but we don't have the k, so it turns out to be not that difficult. Okay, finally we only have this gradient, the curl of f to be negative 2k. Negative 2k. So what does negative 2k means? ijk, k is the z-axis component. This is the z-axis component. Okay, so the right side is x-axis. Okay, y-axis is pointing upward. What is z-axis? Z-axis should follow the right-hand rule. Okay, so you use your finger pointing to the x-axis, cross to the right axis, your thumb is pointing to the out of the page. Okay, so this is z, this is z. So negative 2k it means that it is pointing into the page. Okay, negative 2x is pointing into the page. So which means that if you use your thumb pointing into the page, your four fingers are like rotating clockwise. So this obeys the right hand rule. Okay, obeys the right hand rule. So it tells you this is the rotational axis, is the negative z axis, and then follow this rotational axis to rotate clockwise. Okay, so this is more or less the curl tells you. Okay, yeah. So, okay, after introducing divergence and curl, okay, actually we can go to the main topic, which is the divergence theorem and also the Stokes theorem, and then finally we can derive the differential form of the Maxwell equation. Yeah, but before that, maybe we can